Now I would like to explain about the magnetic field intensity due to toroid and magnetic force concepts. So first, magnetic field intensity due to toroid. This is toroid construction. It having n number of turns. This is capital N, and it carrying a current of I amperes. So the main difference between solenoid and toroid. So solenoid and toroid both are electromagnets, but in case of solenoid, the magnetic material in rectangular shape. But in case of toroid, the magnetic material shape in circular shape. So this is circular magnetic material. So that's why it is called toroid. It having n number of turns, and it carrying a current of I amperes. So now we have to find the magnetic field intensity due to this toroid. So in electromagnets mainly, the total magnetic field present in magnetic materials. So the magnetic field intensity exists only inside the magnetic material. Here this circular construction is magnetic material. So the total magnetic field intensity present inside this magnetic material. So by applying Ampere circuit law, we can find the magnetic field intensity expression. So first to draw an Ampere path. So this dotted line circle indicates the Ampere path with radius equals to r meters. So by applying Ampere circuit law, we know that Ampere circuit law formula closed line integral h bar dot dl bar equals to in closed. Here closed path is circular path and its radius equals to r meters. So only toroid, inside only the magnetic field intensity present. So the total magnetic field intensity inside the toroid equals to h. So next closed line integral dl bar. Here the differential length of the Ampere path equals to dl bar. So total length of the Ampere path equals to, so circle circumference formula, here radius equals to r meters. So total length of this Ampere path equals to circular Ampere path equals to 2 pi r. So h into 2 pi r. So next I enclosed. Here the current in each turn equals to I. The number of turns of the toroid equals to n. So total current enclosed by the Ampere path equals to n into I. So h equals to ni by 2 pi r. So next the direction of the magnetic field intensity. Here assume type of coordinate system, cylindrical coordinate system. So in this direction, so inside the one dotted lines are there. The direction is pi direction. So the magnetic field is present inside the magnetic material and its direction is pi direction. So by applying right hand thumb rule, we can find the direction of the magnetic field intensity inside the magnetic material. So according to right hand thumb rule, the magnetic field intensity direction is pi direction. So unit vector equals to pi direction unit vector equals to a pi bar. So finally h bar, the magnetic field intensity of toroid equals to h into a pi bar. It equals to ni by 2 pi r into a pi bar. Units are ampere turns per meters. So next one, magnetic force. So the magnetic force can exist only when the charge is in motion in magnetic field. If charge is moving in a magnetic field, then only it having the magnetic force. So it is represented by Fm. So Fm bar equals to formula Q into V bar cross B bar. Here Q is charge, V bar is velocity of the charge, B bar is magnetic field flux density. So this is the magnetic force expression. Fm bar equals to Q into V bar cross B bar. So next one, Lorentz force equation. Next topic. So generally it is used to find the total force acting on moving charges. The force on a moving charge equals to sum of the electric force and magnetic force. If a stationary charge present in a magnetic field, it having electric force. If a moving charge present in a magnetic field, it having magnetic force. If a moving charge present in magnetic field, it having both magnetic force and electric force. Here total force equals to electric force plus magnetic force. So first one, if a stationary charge in a field, it having electric force. If a stationary charge in a magnetic field, it having magnetic force. If a charge moving in a magnetic field, then it having both electric force and magnetic force. Here total force equals to F bar, it equals to electric force plus magnetic force. So we know that the electric force equals to formula Fe bar equals to Q into E bar. So according to Coulomb's law, F equals to formula Q1 Q2 by 4 pi epsilon r square. So here Q2 by 4 pi epsilon r square equals to E bar. So Fe bar equals to Q into E bar. So the magnetic force Fm bar equals to Q into V bar cross B bar. So finally the total force F bar equals to Fe bar plus Fm bar. It equals to, so Q into E bar plus Q into V bar cross B bar. So the Lorentz force equation F bar equals to Q into E bar plus V bar cross B bar newtons. So this equation is called Lorentz force equation. So the Lorentz force equation is used to find the total force acting on moving charge present in a magnetic field. So next one, current elements. Okay, current elements. For a straight conductor, current element is I into dl bar. Surface type of conductor case, current element equals to K into ds bar. Volume type of conductor case, the current element is J into dV. Here I is current, dl bar is differential length of the line conductor. Here K is current density and ds bar equals to surface differential surface area. So next J is, so volume current density, dV is differential volume of the volume type of conductor. So this is called current elements formulas. Straight conductor case, current element equals to IDL bar. Surface type of conductor case, K into ds bar. Volume type of conductor case, J into dV. So next topic, the force on a straight current carrying conductor placed in a magnetic field. Here straight current carrying conductor placed in a magnetic field. The magnetic field flux density equals to B bar and the current flowing through the conductor equals to I. Length of the conductor equals to L meters. So let a current carrying conductor in a magnetic field having flux density B bar. So now consider a differential length of the current carrying conductor. That means let consider a current element I into dl bar. So the magnetic force due to current element is dFm bar. Here current element case, so the magnetic force is called differential magnetic force. It is represented by dFm bar. So we know that Fm bar equals to formula Q into V bar cross B bar. Here differential magnetic force. So we are considering only current element. So current element charge value equals to dq. So differential magnetic force dFm bar equals to dq into V bar cross B bar. So equation number 1. The current element formula I into dl bar. So we can write current I equals to dq by dt. So rate of change of charge equals to electric current. So I equals to dq by dt. So dq by dt into dl bar, or it equals to dq into dl by dt. So length by time, differential length by differential time, it equals to velocity. So it equals to dq into v bar. So it means I into dl bar equals to dq into v bar. So equation number 2. So now substitute equation 2 in equation 1. So dfm bar equals to dq into v bar equals to idl bar. So idl bar cross b bar. So the above expression is called magnetic force on current element. Magnetic force on current element. So by integrating the above expression, we can find the magnetic force on a straight current carrying conductor. The magnetic force on a straight current carrying conductor, Fm bar equals to integral dFm bar, it equals to integral idl bar cross b bar. So Fm bar equals to integral dl bar equals to L bar. So Fm bar equals to I into L bar cross B bar. So L bar cross B bar equals to LB sin theta. We know that formula A bar cross B bar equals to AB sin theta into normal unit vector. So similarly L bar cross B bar equals to LB into sin theta. So Fm bar equals to BIL sin theta into An bar. So force units are newtons. So the maximum value of magnetic force equals to Fm equals to BIL. So at theta equals to 90 degrees. At theta equals to 90 degrees, the force is maximum and its value Fm equals to BIL. The next topic, the magnetic force between two straight current carrying conductors. So consider two current carrying conductors having lengths L1 meters and L2 meters respectively. Here two current carrying conductors, first conductor, next one second conductor. So first conductor current I1, second conductor current I2. So assume the current direction in same direction and upward direction. Here I1 I2 both are flowing in upward direction. So assume the magnetic flux density produced by the current carrying conductor B1 and B2. So we know that the current carrying conductors produces the magnetic field. So assume here the first conductor magnetic flux density equals to B1, second current carrying conductor magnetic flux density equals to B2. So we know that the maximum value of the magnetic force Fm equals to formula BIL. So now by using this formula, so we can find the force on each conductor. So first the magnetic force on first conductor, Fm equals to formula BIL. So here F1 equals to, so B2. So this first conductor present present in second conductor magnetic field. So it having some magnetic force. That force equation equals to F1 equals to, so second conductor flux density, first conductor current into first conductor length. So B equals to mu into H. So B2 equals to mu into H2. So here the distance between the conductors equals to d meters. So the magnetic field intensity due to straight current carrying conductor H bar equals to formula I by 2 pi r. If r is the distance between conductor to point P, then the magnetic field intensity H equals to I by 2 pi r. So here the distance between the conductors equals to d meters. So the magnetic field intensity of a first conductor, the magnetic field intensity of a first conductor is I1 by 2 pi d. So similarly the magnetic field intensity of a second conductor is I2 by 2 pi d. Here B2 equals to mu into H2, H2 equals to I2 by 2 pi d. So finally B2 equals to mu into I2 by 2 pi d. So F1 equals to mu into I2 by 2 pi d, I1 into L1. Or it equals to mu into I1 into I2 L1 by 2 pi d newtons. So next find the magnetic force on second conductor F2 bar. So F2 equals to, so first conductor magnetic flux density B1, second conductor current, second conductor length. So here we are finding the second conductor magnetic force. So the second current carrying conductor present in first conductor magnetic field. So it experience some magnetic force. It equals to F2. F2 equals to B1 into I2 into L2. So B1 equals to mu into H1. So H1 is first conductor magnetic field intensity. It equals to I1 by 2 pi d. So B1 equals to mu into I1 by 2 pi d. F2 equals to mu into I1 by 2 pi d, I2 into L2. So force on first conductor, force on second conductor. So here find the magnetic flux direction by using right hand thumb rule. Here both currents flowing in upward direction. So apply the right hand thumb rule and find the magnetic flux direction. So by here the magnetic flux direction according to right hand thumb rule, anti-clockwise direction. So between the conductors, the magnetic field direction. So first conductor magnetic field direction upward direction, second conductor magnetic field direction downward direction. So between the conductors, the magnetic fields are opposite directions. So it creates the two different magnetic poles. So for example, if this magnetic field produces north pole, it creates south pole. So between the conductors here, two opposite magnetic poles created. If two opposite magnetic poles are created, then there exists an attractive force. So here the type of force is attractive force. So the total force F bar equals to F1 plus F2, F1 plus F2. So final equation mu into I1 I2 by 2 pi d into L1 plus L2. So by adding these two equations, so we get the total force equation. So units are newtons. So if I1 I2 are in opposite direction, here we taken current direction, same direction. If I1 I2 are flowing in opposite direction, then there exists a repulsive force between the conductors. If these two currents are opposite direction between the conductors, so same direction magnetic flux is present. So in that case, so same magnetic poles are created between the conductors. If same magnetic poles are created, then there exists repulsive force. In that case, the total force F equals to F1 minus F2. So force equation, repulsive force equation, mu into I1 I2 by 2 pi d, L1 minus L2 newtons. So this is attractive force equation. This one is repulsive force equation. If current same direction, there exists attractive force. If currents are in opposite direction, there exists repulsive force.